So we're moving on to one of the hallmarks of Calc 1, and that's related rates. And all related rates are our application problems for implicit differentiation. So everything we just talked about in the last video, we're going to talk about again and start to apply it. Well, because they're application problems, we should review some good problem solving skills as well. And they're these. We should start by identifying our given information. And one of the ways we can do that, we should just try to isolate it from the paragraph. Just try to pull it out of the paragraph so that way the information is easy to access and you don't have to go trying to sift through all the words again to try to find what's important. The next thing would be to identify our goal. We need to figure out where we're ending up. What am I solving for? A lot of times this can give us a hint or a look into how the problem is going to work. If I know what my end goal is going to be, sometimes I can kind of reverse engineer the problem in order to figure out how to actually solve it. With these problems, we're not always given our variables, so we want to pick logical variables just to avoid any confusion. This is not the time to get inventive. These are things just like V for volume, C for cost, T for time, R for radius. Logical things so that we know what we're dealing with. We want to kind of think about these just as abbreviations. Just as we would abbreviate logically, we're going to pick logical variables as well. And if necessary, and it's often necessary, we should draw a picture to try to see actually how things are related, try to get things written somewhere. Sometimes that visual can be really helpful. So let's take a look at a problem. Air is being pumped into a spherical balloon so that its volume increases at a rate of 100 centimeters per second. So this notation here is just IB's way of writing centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So there's a lot going on here, but let's try to dissect it a little bit. So we know we're dealing with a spherical balloon. So what are we given? We're given a spherical balloon. And we're told that its volume increases at a rate of 100 centimeters per second. So volume increases at 100 centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? So we're also given that the diameter is 50 centimeters. Diameter is 50 centimeters. And we're being asked to find how fast the radius of the balloon is increasing. Well, that sounds a whole lot like a rate of change. So our goal is the rate of increase of the radius. So here's our given information, here's our goal, and now let's try to see if we can connect it in some way. So if we're given a spherical balloon and we're asked to talk about its volume, well then I know the volume of a sphere is 4/3 pi r cubed. And if I'm talking about the rate at which the volume is changing, then rate of change is slope is calculus, right? So that's the derivative. So the derivative of volume with respect to time. So the change in volume, dv, with respect to time, dt. And we know that's equal to 100. That's what we're given. Oh, you know what? This should have said centimeters cubed per second, actually. Sorry about that. That's a typo. Centimeters cubed per second. And we're also given that the diameter is 50 centimeters. Well, the word diameter should raise some red flags because every time we do anything usually with volume, we're dealing with the radius, and that's what we have here as well, right? So if I'm given diameter, most of the times the first thing I should do is change this to radius. I'm just going to put my units in here as well. And we're asked to find the rate of increase of the radius. which again, if we're talking about rates, then we're talking about derivatives. So the rate of change of the radius dr with respect to time, dt, and that's what I'm being asked to solve for. I like to get a picture, so let's get a diagram going. Here is my sphere. It has a radius. I'm just going to mark the radius in because that's usually more helpful. It has a radius, and we know that that radius is equal to 25 centimeters. We know that, actually I'm going to keep the same color, that the volume is given by 4/3 pi r cubed, and that the rate of change of the volume with respect to time is 100 centimeters cubed per second. I'm being asked to solve for the rate of change of the radius. Usually with these problems, once I get this, once I have an equation, an explicit equation, that's the thing I'm going to work with. So we're going to start here, right? Because that's got all the things that I know. It's got my volume, it's got my radius, and what I need to do is find a way to introduce what I'm trying to solve for. How do I introduce my dv by dt, and how do I introduce dr by dt? Well, the way we're going to do that is by deriving implicitly. We're going to derive everything with respect to time. And this is implicit differentiation, right? Because my variables don't match. So the derivative of volume with respect to time is just dv by dt. And just like we did with implicit differentiation before, the same thing's going to apply over here. So derive like normal. I'm going to get 4 pi r squared. But my variables don't match, so I'm going to account for that with my differential term, dr by dt. And now it's just a matter of plug in what you know and solve for what you don't. So dv dt is 100. Radius is 25. Sorry, it's 25 squared. And I'm solving for dr dt. And if I just do that real quick into my calculator, 4 pi times 25 squared, I get dr dt. So the rate of change, the rate of increase of my radius, 0.013 with 3 significant figures. Sorry, 0.0127 with 3 significant figures. Centimeters per second. So units are key here. We want to make sure we have clear units when these application problems. So 2 things to remember for IB, right? 3 significant figures, and remember your units as well. Let's take a look at one more problem. Another classic problem for related rates. A 13-foot ladder is leaning against a wall when its base starts to slide away from the wall. By the time its base is 12 feet from the wall, the base is moving at a rate of 5 feet per second. At what rate is the top of the ladder sliding down the wall at this moment? I like to start with a picture here. Oops. Because there is a lot of information. So here's my wall, and here's the ground. And here is my ladder. So I have a 13-foot ladder, and its base starts to slide away from the wall. So the base is moving maybe this way. Should I pick a more distinct color? So my base is moving away from the wall. By the time the base is 12 feet from the wall, the base is moving at a rate of 5 feet per second. So something's going on over here at a rate of 5 feet per second. These are all feet. At what rate is the top of the ladder sliding down the wall in this moment? So again, there's some kind of a downward motion here. And I don't know what this rate is. And actually, at the moment, I don't really know this length either. Since it's horizontal, since it's vertical, I'm going to call it y. So let's start to put some of these into math terms. What are we given? We're given a 13-foot ladder we're given this 12-foot distance, so that looks like horizontal distance, right? X equals 12. When x equals 12, the rate of change of that horizontal distance is 5 feet per second. So let's call it dx by dt, the change in horizontal position with respect to time. It's 5 feet per second. At what rate is the top of the ladder sliding down the wall at this moment? So my goal is to figure out the rate of vertical change with respect to time. Well, based on the picture, I have a right triangle. And in this case, I'm not immediately given an equation, but I know one for right triangles. I know the Pythagorean theorem, right? So x squared plus y squared equals z squared. So let's actually work with that, right? The thing I know, the big thing here is the Pythagorean theorem. X squared plus y squared equals z squared. I need a way to introduce dy by dt. So let's derive this all with respect to time. And most of the times when you do related rates problems, you are going to derive with respect to time. And it does end up being implicit. So I get 2x dx by dt. That's good, I have both of those. I have 2y dy by dt, that's good, I need to solve for dy by dt. And I have 2z dz by dt. And now it starts to look problematic because I don't know dz by dt. And actually, come to think of it, I don't know y right now either. And I'm solving for dy by dt. And it might right now look like there's too much. There's too many unknowns. Fortunately, there aren't too many unknowns. We can solve for y, right? We know the Pythagorean theorem. Actually, I'll stick with some different colors here. We know the Pythagorean theorem, so I can solve for y. 12 squared plus y squared equals 13 squared. And if my Pythagorean triplets still work, if I can remember them, I believe that missing side is 5. It is. Y is 5. So there's one unknown. And now this dz by dt, well, my ladder is a fixed length, right? So we figure this one out. My ladder is a fixed length, so nothing that happens over time is going to change the length of that ladder. So the ladder's length is constant, and the derivative of a constant is 0. Right, so the ladder's length is constant. No matter what happens, right, the ladder is still the same length. So the rate of change of the ladder is 0. So at this point, I know all my information, so now I can go ahead and plug stuff in. So 2 times 12 times 5 plus 2 times 5 times dy dt is equal to 2 times 13 times 0. So I'm just plugging everything in. To simplify, so I have 120 plus 10 dy by dt equals 0. And I'm going to get dy by dt is equal to negative 12 feet per second. Again, units are important. And you might be thinking to yourself, what's going on with this negative here? Well, rates of change indicate directions. So this is telling us it's moving down, right? That negative indicates it's moving down. So the rate of change of the vertical height, right, is negative 12 feet per second. But we could also say that it's moving down at a rate of 12 feet per second. So these are related rates problems, right? We need to find a way to introduce variables. We need to find a way to introduce what we're solving for. The best thing you can do is stay organized.